So, in this module we will talk about scheduling algorithms. So, what we completed till the earlier module is the need for a scheduling. So, there are 3 queues as we had seen. One is a ready queue, one is the running is not a queue, and there is a waiting queue. So, there can be processes which can be readily scheduled, which are ready for execution, and it can be scheduled. Then there are processes which have asked for some disk IO, they will be in the waiting queue. The operating system will go and that disk IO or whatever is complete, the service is complete, then again it will be moved back to the ready queue, and again a scheduling decision will be taken and it will again come back and start executing whenever it is scheduled. So, as a process, when I am created, I go to the ready queue, then the scheduling algorithm which we are going to see in this module will look at me, and if it feels that I should be the next fellow to run, it will make me to the running state, it will allow me to execute on the CPU. And then I may ask for say operating system service. Once I ask for that service, then I will be moved, there will be a context switch, my process control block will be saved and I will be moved from the running state to a waiting queue. I will wait there till the operating system finishes my service. After the operating system finishes my service, I will be again put into the ready queue, I will be again put into the global thing, and there again the scheduling algorithm, if it finds me suitable, it will again schedule me. So, this is how as a process I will work. But as a process, when I am executing, there is an external interrupt, right, for some other reason, and I am not responsible for it, then I have not asked for any service. So, immediately I will be moved from the running state to the ready queue, and when I moved, again my process control block, everything will be saved. If I am not executing, my context will always be in my process control block. So, again I will be in the running queue, again the scheduling algorithm, whenever it finds me suitable, it will go and schedule me into the CPU. So, this is how the whole thing is working. So, the notion of a scheduling algorithm, as we had seen in the previous module, is that I want to go and maximize throughput, I want to go and maximize several things as we saw. So, I want to maximize my CPU utilization, I want to maximize my throughput, I want to minimize my turnaround time, I want to minimize my waiting time, I want to minimize my response time. So, for all these criteria, the scheduling algorithm will work based on this criteria to select the next process that needs to be scheduled onto the CPU, right. So, some of the few things that we need to remember is that first one reason for multi-programming, why more than one task need to execute at the same point of time, so that all these processes wait for less on an average, and so I will get more response, right. So, it is like multiple fellows log into a mail server, every fellow should get some time on the CPU, then only you will feel that you are being served by the mail server. If one fellow finishes, then only the next fellow should start, then there is no way by which this responsiveness can be created. So, what is multi-programming? The degree of multi-programming is the number of concurrent processes that are admitted into the system. It is the sigma of the number of processes in your ready state and your waiting state plus what is executing. So, that is called degree of multi-programming, and if the degree of multi-programming is large with a good throughput, that means every program will get a good response from the system. The second reason for multi-programming is to improve hardware utilization, as that we have already seen between a disk and a CPU, we gave some examples. Many of the applications use only one system component at a time. For example, they use either the CPU or the disk. So, if I have multiple components, then each one will use one of these, and so the entire hardware utilization will go high. And the important thing is that I need to have a good mix of jobs which would use different components of the system, and I get maximum hardware utilization and also meet some of the criteria that we had mentioned in the previous modules. So, let us look at the different scheduling algorithms very quickly. Now, this is a notion of a single job. We have explained this in the previous module, I will just explain it for the sake of revision. A single job basically executes on the CPU, it also executes on the disk. Sometimes it is on the CPU, sometimes it is on the disk. Whenever it is on the CPU, the disk is idle, whenever it is on the disk, the CPU is idle. If you have multiple jobs, when the first job uses the CPU, the second job can essentially use the disk, and when the first job uses the second job uses the CPU, the first job can use the disk. By this, please note that the empty white space white space is idle time, the amount of white space in the top in the context of single job, what you see on the screen, is much more than the amount of white space that you see in the bottom in the context of multiple jobs, essentially implying that I have better hardware utilization. Now let us look at some of the timing. So a job arrives and it actually waits in the running queue, it waits in the ready queue, and it starts running and it terminates. So that amount of response, T response time, is the average time from submitting a job until it terminates. This is the sum of the time spent waiting in the queue and the time actually running. In the context of real time systems, this gets a small deviation. The response time is the time between time of starting minus the time of arrival. Okay, so that is also called the first response time. Generally people are interested in reducing this response time because they want the result to be done within as early as possible. So the role of a scheduler, we had seen the role of the scheduler in great detail in the previous lecture, but I am just summing up, is that there is a ready queue, and from the ready queue it has to look at all the processes and it has to select the next process that needs to go and get scheduled onto the CPU, and that is the role of the scheduler. So there are many scheduling algorithms, the first come first serve, the shortest job first, the shortest remaining time first, non-preemptive priority scheduling, preemptive priority scheduling, round robin, highest response ratio next, multi-level feedback queue scheduling, multi-level queue scheduling algorithms. So these are some of the different algorithms that we had, scheduling algorithms that are of use, and we will see some of them as we go. The first come first serve scheduling is the simplest, where a job comes, it starts executing. Please note, see the timing diagram on the top. The job 1 arrives and it is executing. Before it finishes, job 2 comes and it waits. Before even job 1 finishes, job 3 comes and it also starts waiting. Once job 1 finishes, job 2 runs. After job 2 finishes, job 3 runs. So the overall waiting time is, job 1 does not wait for any time here, that job 2 waits for, actually you see 4 units of time, while job 3 waits for 4 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16 units of time or 13 units of time. So the overall waiting time for job 3 is quite high. It waits for 13 units of time to execute 2 units of time to finish. So this is about the first come first serve. So if I have a large process, then what happens is some short processes that are following it will have to wait for long. So that is the basic drawback of first come first serve. If every process is of short duration, then this responsiveness would be quite high, but now you see that job 3 is a very quick job, but maybe of very all small jobs are very highly prioritized, but it needs to wait for lot of time, at least 3 times its execution time, 3 or 4 times its execution time, actually 6 times its execution time. It needs to wait for it to start running. From the point job 3 arrives, from the point it starts executing, at least 12 units of time are spent. The FCFS, as we see, is non-preemptive. So when job 1 gets in, it completes, then only job 2 comes. So the FCFS is very good for what we call as batch processing, where we submit the job and tomorrow morning we come and take it, or but it is not good for time sharing in systems where your response time need to be fast. Now what is an ideal case of scheduler? So look at this, when job 1 comes, it starts executing, job 2 comes, it also starts executing, job 3 comes, it also starts executing. So if job 3 needs say 10 units of time, it should finish off in 10 units. So when there are k jobs in the system, they all run simultaneously but at a rate of 1 by k. This is what we need to finally simulate, right. So when job 1 is executing, it is completely owned by the system. When job 2 arrives, then the resources are split between job 1 and job 2. When job 3 arrives, then the resources are split between job 1, 2 and 3. When job 3 finishes, again the resources are split between job 1 and job 2, and when job 1 finishes, the entire resource is given to job 2. So this is how, as you see on the top, this is an ideal case, and these type of scheduling algorithms are basically called as round robin, which basically says it gives a time slice. So if I have k processes, then it divides the time slice among these k, it gives 1 k 1 by k for each, and basically does. So, this is basically possible using a concept called round robin scheduling. So, these are all the metrics that we need to see. We have a wait time, we have response ratio or slowdown, we have throughput, and we have utilization. We have seen the difference between throughput and utilization in the previous lecture. Throughput is the number of jobs that we finish at a unit time, but utilization is amount of time I use a CPU. Throughput and utilization together will talk more about what we call as the wait time. The wait time is the amount of time the job waits in the ready queue for it to get scheduled, and we need to minimize this wait time. And there is also something called response ratio or slowdown, which is nothing but the ratio between T response divided by T runtime, right. This is the ratio of the response time to the actual runtime, and this is very, very important, and this normalizes all jobs to the same scale, right. And so by this we could basically get an understanding of how each job should be treated. So, for example, if I have a long job, I can wait a bit more, and if I am having a short job, my response ratio will be a little higher, and so I need to finish faster. So, this response ratio can be used as an important parameter for me to basically go and make a scheduling decision. So, these are all the metrics here. Now, some of the good algorithms that we see is, one is shortest job first scheduling, the non-preemptive scheduling. We could have a preemptive flavor of this also. So, biggest challenge here is that I need to know, so if I have a collection of job, I have to find out which job will finish fastest or which job needs the least amount of time, and that shortest job is the one I will go and assign it to the CPU. Now, the biggest challenge here is that I need to know the exact time, the next CPU burst of that program, right. How will I estimate this CPU burst? So, there are some statistical methods for estimating this CPU burst, which there are some averaging methods, exponential averaging methods, which will be doing this. And so, the shortest job first scheduling is basically a non-preemptive algorithm which uses statistical methods to basically find out the value of the next CPU burst, and out of all the CPU bursts computed for all the processes in the ready queue, I will find the one with the minimum value and I will schedule it next. I could have a preemptive flavor for this shortest job first scheduling algorithm also, where we change the processes if the next CPU burst is less than what's left of the current one. So, this is very interesting scheduling algorithm. And there is also an algorithm which is called shortest remaining time first. So, this is a very nice case study what you see on the left hand side. Now, a long job is running in the shortest job first, since it is non-preemptive, at say that start position, a long job is actually running and a short job also comes at that point of time. It needs to wait for the long job and then the next short job has to take. When the long job started executing, the short job was not there. So, long job got scheduled because it was the shortest job first, and when the short job came in, then it had to wait. It came at the position of start and it had to wait for long and then it starts executing. So, the average wait time, as you see, is somewhere very high from start, right, because the short job actually waited for quite long amount of time, right. But in a shortest remaining time first, it is a preemptive algorithm. When the short job came at the start position, see on your left hand side the figure below, the short job came at when the long job was executing, the short job came, and once the short job came, immediately it was admitted by the scheduler, and the scheduler now went ahead and made another decision of whom it should schedule. At that point, it found out that the long job will take more time than the short job. So, the remaining time for the long job is much larger than the remaining time for the short job. So, the short job got scheduled first and then the long job. So, the average waiting time now got reduced, and as you see that the average waiting time has reduced in this case. So, the shortest remaining time first is a preemptive algorithm, while the shortest job first a non-preemptive algorithm. So, this basically gives you the difference between preemption and non-preemption, and certainly preemptive algorithms can reduce your average wait time. So, with this we come to the end of scheduling algorithms. From a security point of view, scheduling algorithms, you need to understand what is scheduling and what are the different things that happen during a context switch, and that is more important from a security perspective. Maybe there is also some notions of how do you handle certain denial of service things, carefully looking at the scheduler, because the scheduler is one which is going to basically get certain things running up. So we will discuss about that later in some later course, not even in this course, but as of now understanding scheduling is very important for understanding the operating system per se and also networking, and that is why we have covered a brief of scheduling algorithms. In the next module we will deal about something much more important than this called process synchronization in great detail. Thank you.